In this video, we will explore topological sorting using Kahn's algorithm and depth-first search, also known as DFS. A topological sort is a linear ordering of vertices in a directed acyclic graph, often abbreviated as DAG. This means that for every directed edge, represented as U, the vertex U comes before vertex V in the ordering. For example, one possible topological order for the illustrated graph is 1, 3, 2, 4, 5, 6. Topological sorting has several key properties in real-world applications. Firstly, topological sorting is only possible for directed acyclic graphs or DAGs. A graph with a cycle cannot have a valid topological ordering. Secondly, DAGs always have at least one vertex with no incoming edges. Finally, a DAG can have multiple valid topological orderings. In terms of real-world applications, topological sorting is used in task scheduling with prerequisites, course prerequisites in academic planning, dependency resolution in build systems, and data processing pipelines. Kahn's algorithm provides a method for performing topological sorting. The algorithm steps are as follows. First, identify all vertices with no incoming edges, also known as indegree equals 0. Second, add these vertices to a queue or any suitable data structure. Third, while the queue is not empty, remove a vertex from the queue, add it to the topological ordering, remove all edges from this vertex. Then, if any vertex now has indegree equals 0, add it to the queue. Finally, if all vertices are visited, return the ordering. As you can see in the example, node 1 has indegree of 0 and we can start building the topological order with this node. Here is the Python code implementation of Kahn's algorithm. The function is called Kahn_topological_sort, and it takes the graph as an argument. First, we count the indegrees of all vertices. Then, we create a queue with all nodes that have an indegree of 0. We initialize a result list for the topological ordering. Then, we process until the queue is empty, in which we remove an element from the queue, append it to topological order, and then for all the neighbors of the current node, we reduce the indegree by 1. If any neighbor's indegree becomes 0, it is added to the queue. Finally, we return the topological order. Another way of doing topological sorting is by using depth-first search or DFS. The algorithm steps are as follows. First, create a temporary stack. Second, mark all vertices as not visited. Third, for each unvisited vertex, call the DFS helper function. The DFS helper function does the following. Mark the current vertex as visited, recursively call DFS for all adjacent vertices, push vertex to stack after all neighbors are visited. The stack contents in reverse order give the topological sort. In the example, node 1 is marked as visited, and node 2 is the current DFS node. Here is the Python code implementation of the depth-first search algorithm for topological sorting. We define a function called DFS_topological_sort that takes graph as the argument. Inside this function, we keep track of the visited nodes in the visited variable. A stack is initialized to keep track of the topological order. The recursive function DFS takes a node as the argument, marks the node as visited and calls itself on all the neighbors of the node. After visiting all of the neighbors of a node, we push the node in the stack. At the end, we need to process all the unvisited nodes by calling the DFS function on them, and return the reverse stack. Here is the comparison of Kahn's algorithm versus the depth-first search approach for topological sorting. In terms of time complexity, both have the same complexity, which is order of V plus E, where V is the number of vertices and is the number of edges. Space complexity is also the same order of V. Kahn's algorithm is iterative and uses a queue, while depth-first search is recursive and uses a stack. Cycle detection is easy to implement in Kahn's algorithm, but requires additional states in depth-first search. Finally, edge case handling is explicit in Kahn's algorithm through indegree tracking, and implicit through recursion in depth-first search. Topological sorting has many real-world applications, including scheduling jobs or tasks with dependencies, building systems such as compilation order, course prerequisite planning, package dependency resolution, data processing pipelines, and critical path analysis in project management. The complexity analysis for both Kahn's algorithm and the depth-first search approach is as follows. Both have a time complexity of order of v plus e and a space complexity of order of v, where v is the number of vertices and is the number of edges. Therefore, both methods are optimal for graphs. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.